Galaxy clusters are the most massive structures in our universe. Dark matter accounts for 85% of the mass in galaxy clusters. Studying galaxy clusters therefore tells us about dark matter, structure formation, and key questions in cosmology. In this video, we introduce our method to estimate the surface mass density of galaxy clusters. One of the most powerful proofs of mass is through gravitational lensing. The cluster's enormous mass curves spacetime, so light from background objects is deflected and appears distorted to the observer. The most massive clusters, with 10 to the 14 or 15 times the mass of our Sun, produce many strongly lensed images. These tightly constrain the cluster's surface mass density. Smaller clusters of around 10 to the 13.5 or 14 times the mass of our Sun produce far fewer lensed images, making accurate mass estimation much harder. We introduce an automatic method to reconstruct the surface mass distribution of galaxy clusters. Our generative pipeline is constrained by our gravitational lensing forward operators. But for smaller clusters of 10 to the 13.5 or 14, lensing information alone is insufficient to fully recover the mass distribution. Thus, we combine these operators with our learned diffusion-based prior. We also present Dark Cluster 15K, our dataset of 15,000 simulated galaxy clusters used to train our prior. Dark Clusters 15K provides mass and photometry maps. These two quantities are correlated. Other works might even assume a one-to-one relation between light and their estimated mass. In contrast, our diffusion prior learns the distribution of mass condition of the observed photometry, which allows it to learn complex relations. We use Dark Cluster 15K to evaluate our work and hope it can serve as a benchmark for future research. In summary, our generation pipeline combines gravitational lensing constraints and a learned mass prior condition on the observed photometry. In our evaluation, our approach accurately estimates galaxy cluster structure. Our framework produces samples from the full posterior distribution, allowing us to quantify per pixel uncertainties and confidence estimates. Our approach can generalize to galaxy clusters at different redshifts, which correspond to younger and older cluster population outside of the training distribution. In addition, we created a test set using different simulations than our training data. This shows our method can generalize to unseen scenarios. We also tested our method with real data. Here is our method's estimate of the mass distribution in the MAX 1206 cluster. Other methods either rely on simplified parametric models or handcrafted pipelines requiring expert tuning for each cluster. Upcoming surveys will discover tens to hundreds of thousands of clusters, so automated methods like ours will become essential. Thank you for listening.